Welcome to week 5, day 2. We are going to be starting a brand new topic today. I'm not going to be talking about your homework, which is due next Monday. Again, if you need a partner, message me. I'm not really going to be talking about that today. We're taking on a brand new topic today. That topic is linked lists. Now, I know that you've done some zyBooks on them already, and I did that deliberately because they're a hard subject to understand, and I figured that if you had done the reading first, which is a weird concept that a lot of college professors want, like they want the students to do the reading and then come to class prepared, like, which nobody ever does. At least I can kind of enforce that by having the zyBooks due before my lecture on the subject. So hopefully it'll give you enough of the background information that it doesn't melt your brains too much, because linked lists are not easy to wrap your brain around, even though they're not really that much code. Whenever you deal with recursion, your brain just starts leaking out of your ears, and like the gears in your brain like lock up. You're like, what is going on? Your face melts like you've seen the Ark of the Covenant. So you tricked us into being prepared. I know. My favorite example of that was I used to run an after school program for poor kids in what you'd call the ghetto, San Diego. And we're teaching history. So every Wednesday we'd come down and teach history to the kids. And we started, we got sponsorships from like local businesses. Like McDonald's donated gift certificates for like free fries. And we got like, the cool little pencils that had like the glitter on them and stuff like that. And so when students did well in the quizzes, we just kind of hand them out like, yeah, boom, here you go, good, boom, boom. And that got them really interested in it, And then one of the kids figured out that we were just going through the textbook, like one chapter per week. Like, we're going to talk about the Civil War, right? And so this kid was like, oh man, if I read the next week's textbook before they teach it to us, I'll get all the questions right, and I'm going to be rolling in the French fries. And he did. And then all the other kids were like, how did you do that? And he's like, I cheated. I read the textbook before the class. And they're like, oh. And so they all started cheating too. And they all started reading the textbook too. And they came in, they had this really smug look on their face, like, I'm like, who was the president during the Civil War? They're like, Abraham Lincoln. I'm like, what? How did you know that? And they're like, and I'm like handing out French fries like Santa Claus, And they just thought they had really pulled a fast one on me, And they were like, next week, are you going to be talking about Reconstruction next week? I'm like, I don't know. You'll just have to show up and find out. And they all came in having read the entire chapter on Reconstruction. Like, you could hear them before class, like, all right, where did Reconstruction take place? What states, and when did it end? And I was like, so that's why I had you do the textbooks on linked list first, so that it kind of lays the groundwork. Now we're going to talk about it today. All right. DJ Khalid suffering from success. Exactly. So, yes, I tricked you all into studying. Hopefully you did it. If you didn't, prepare for your brains to lock up a little bit more. Okay. So linked list is our first data structure that we are going to implement ourselves in this class. Up until now, we've been studying object-oriented programming. We've been studying how to use the standard library, the STL and stuff. My tablet just came unplugged again. Get this plugged in here. We are going to start writing a data structure ourselves, so you can kind of learn what it looks like on the inside to do a data structure. Now, this is going to be very long and involved, so this, prepare yourselves, okay? So I'm going to make a struct. Should I be doing this with text? Nah, I'm going to handwrite it. Struct list. And we're going to make a linked list of ints. And this is what makes it a linked list. List, pointer, next, semicolon. There you go. That is a linked list. Okay, that is you have to make your own linked list. There is a built-in linked list class. Yeah, if you want to make a linked list of here, I'll show you the STL version just so you kind of can see what a list is all about. Let me hide my solution to RTX on real fast. Okay. Remember, you can ask for help on RTX On once per person. If you have 2 people in your group, you can do it twice. Send me a meme saying Gondor calls for aid, and I will give you like up to 3 lines of source code to help you on your way. Okay, so the edit. Yeah, I must have had this. Swap file begun. All right. There we go. So if you want to make a linked list just using the STL, and we're going to be actually making a linked list ourselves. Like we're going to be putting on the STL hat and making a linked list in this class. But if you just kind of want to see what a linked list looks like, it looks like this. Make a list of integers named L. I'm sorry, I don't have any better names. And it's going to hold the numbers, I don't know, 10, negative 20, 52. Okay. And so that makes a linked list that holds these numbers in order. And lists are defined really, and this is an abstract data type. Like we actually don't know how the list is implemented in the standard library. Like we could look up the source code and kind of figure it out, but it doesn't matter to us because it's an abstract data type. And ADT and ADT means we don't really know how it's made, right? It's just opaque to us. Like it gives us an interface. And so the kinds of things we can do with a list is we can say l.push back, so we can add the number 1111. So the list is now 10, negative 20, 52, 1111. And we can do things like, did I screw something up here? Vim is just being confused now. Okay. There we go. Vim. Do you see that? Vim wanted a semicolon in the comment, or it wouldn't automatically indent my code. So it's an abstract data type. Yeah, so we don't know how it's done, but it provides an interface. So it allows us to add things to the end. We can delete things off the beginning, pop front if we want. So the list is now negative 20, 52, 1111, and we can look at that, the auto indentation. We can l.push front, we can push back, pop front, pop back, and that's mostly what we use lists for. We usually use them to add and delete off the ends, but also if you have a pointer to the middle, if you have an iterator to the middle of a linked list, you can insert there, like l.insert, and that takes a iterator. So if we did like a find or something, we could say like auto iterator equals l.find 52, and then we could say l.insert, passing in iterator, passing in 1000, and then we can have the list is now negative 20, 52, 1000. I think. I don't remember if it's before or after. No. Find l.begin, l.end 52. But really, this is not very efficient with a linked list, and so this kind of thing, if you're going to be doing repeated inserts in the middle, yeah, we would do this. Mostly, though, just push front, push back, pop front, pop back, that kind of stuff. So do you understand the interface? So if we, let's actually find out which order. I don't remember actually if inserts before or after, so let's find out. So for every integer in the list, see out the integer. And so it comes before the 52. Okay. See how often I use linked lists, which is almost never. Okay. Any questions about this? This is the list type that comes in the standard library. But we are going to be doing our own. So we're not going to be doing the standard library one. We're going to be making our own list class today. Why don't I use them? Because their performance is terrible. it's not a 0% thing, but for me, the number of applications I write that actually use a linked list, it's probably going to be around 2%, somewhere between 0 and 5%, I would say. Yeah, if you want to print out like the 500th element of a linked list, you have to start at the beginning and go to the next 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 and go to the next. You can't just be like, hey, what's element 500? Like you can with a vector, and that is really painful to me. Like I really like that vector. Like, hey, just tell me what element 500 is, and it tells you immediately. What are they used for then if they perform terribly? They're used in situations where you need to insert into the middle of a data structure repeatedly. That is the only use case, or if you need to splice two things together. If you're going to merge two lists together, that could be done in order one time. Whereas I think every other data structure, it's order n to do it. So like if you have one vector and another vector and you want to combine them into one, like you just start at the beginning and go to the end and just kind of push back a bunch of times and do a new one. Linked lists, you can splice them together in order one. You basically have the end of the one point to the next one, and everything's a happy family. So those are the two cases. That's really about it. Push back and push front are useful, but decks do it better. So if all you need are like push front, push back, pop front, pop back, I would use a deck, a double-ended queue. It's a vector that works on both sides. I wouldn't use a list. Decks seems useful. Yeah, I do use decks. Like decks come up like more often than lists, like 20% of the time. What scenario would require you to insert in the middle? Let's say you've got like a word processing document, and you move the cursor here, and you start typing. You're inserting in the middle, right? So if you did that with a vector, think about it. Every time you typed a new letter here, all of the elements below it in the list would have to be shifted right one, and this would be slow. Like if you had like you had Hamlet or something, you started typing really fast, it'd go, and it's trying to move all the letters one to the right repeatedly. That would just, not work. So there's actually specialized data structures called ropes used in word processing, things like that. But of the basic data structures, vector, hash table, set, list, deck, linked list would be the right option for the level that you're at right now, because basically you have to move the cursor around, right? So you have to move the cursor around to a spot, and so the thing kind of goes to the right spot on the linked list, and then you can start inserting. Okay, let's get to it. Okay, imagine a laggy notepad. It's not that implausible. Notepad doesn't work well with large documents. Okay, let's make one. We're going to make a linked list of ints. And that's it. That's a linked list. So every linked list contains a linked list of integers, which is what this is, contains two things. It contains the data held at that point, and it holds a pointer to another list. So every list has a pointer to another list. So each node, each spot in the linked list is actually a linked list, and a linked list points to another linked list. So it's this notion of a recursive data structure that like hurts people's brains a lot. But I'm going to start off by just building it manually, and then I'm going to show you building it like and using functions and things like that to make it kind of go smoother. So let's pop back over into here, and let me draw it out. Give me three numbers. We're going to make a list of three numbers. 420, okay. So the front of the linked list, by the way, we call a head. And I'm kind of drawing this out, but it's going to hold 420. Then it's going to have like a pointer in there. And right now the pointer's not initialized to anything, so I'm just going to have it pointing to something. Who knows? It's not initialized. And then give me another number, pi, so 3. All right, so we got pi, and that's pointing at 3, and its pointer is going to be pointing at, I don't know, nothing. We're not initializing. We don't have a constructor. Probably we should have a constructor, but we don't have one yet. And 96 from Shook. All right, so we will call this meme 96. And this one's also pointing at, who knows, it's uninitialized data. It does not point to null unless you set it to null. I don't have a constructor here, right? Would you like it to be initialized to null? Say yes. Say yes. Do you want me to initialize it to null so we don't have uninitialized memory addresses in here? Okay, yeah, probably a good idea. All right, so if there's nobody after you in the list, you indicate that by setting the value to null. And you can do this in 3 ways. You can set it to 0, you can set it to null, or you can set it to null pointer. Null and 0 are the same thing. Null is just an alias for 0. You'll see this a lot in C, especially. They just set it to 0, or they set it to null, and null is just an alias for 0. In C++, this is kind of the C world way of doing things here, although you will see C++ people do it. This is kind of the approved C++ way of doing things. So you set list pointer next equals to null pointer. And the reason why we like that is because what if you accidentally, like, I don't know, added 5 to 0? You know, that would compile just fine. Whereas if you accidentally, like, tried adding to null pointer or treating it otherwise like an integer, it's its own type. It's its own special null pointer type, and there are no operations defined on it other than dereference, maybe. And so null pointer is sort of, that's what you should use. Okay, and that indicates that there's nobody after us in the list. So my brain equals null. So yeah, let's make a little constructor here. Let's initialize the data to null and the next to null, or be more proper, null pointer, just like that. So nobody follows us, and data is 0 by default. Okay, and then 21. We had 21. Okay, so these people here are no longer uninitialized. Yay, they're not uninitialized anymore. That's good. Good on us. You really don't want to have uninitialized data ever. Ooh, that is not good. All right, so all these fellows are initialized to 0 now, and we had a 21 in here from Betancourt. And so this is going to be the end of the linked list. We're going to call this one tail. So tail is going to be holding 21, and it's also going to be pointing to 0. So this is not a list yet, because they're not linked together. Our topic for today is called a linked list. And so we need to link them together. And we're going to do this by hand at first, so you can kind of understand how it works and see the syntax on it, because the syntax will be a little tricky. So let me just do this all by hand. Let me snap this window over to the left here so I can refer to it when I'm making the code. Okay, so I'm going to make a list pointer called head. Head is going to be equal to new list. So this allocates memory and returns a pointer. Oh no, pointers! Ah! Yeah, it's a reasonable reaction. I'm not mocking you. a big push in C++ from the 90s onwards has been to try to make it so you don't need to use pointers almost at all. And Java, the programming language, was actually made because they considered pointers to be so scary, they just eliminated it from the language entirely. So you can't make a pointer in Java. In Java, it would just look like that. Okay. So we're going to make a head, and we're going to do 4 of these, I guess. So I did that. Comment on each one. So this is head, and then we had pi, and we had meme from Shook, and we had tail from Betancourt. Okay, so now we've allocated. We've got this. This is kind of a picture of what our world looks like at this point in time. We've allocated memory for head. Oh, we haven't set the data yet on it. So all these values are 0 right now, and all the pointers are pointing to 0. That's where we're at right here. Are we leaking memory currently? Yes or no? With what we have on here on the screen. You don't know? You know, me, Curly. You know. Pointers are the boogeyman of Java. Yeah. It's like John Wick. Pointers are like John Wick. You need to delete if there's a new. Yeah, so we should probably, let's just get that taken care of right now, just so we don't forget. So we'll delete head and YY3P, and just go ahead and do this real fast. And if you see Y like Vim, you know, yeah, that's Y like Vim. Makes doing stuff like this very easy. So yes, we need to delete these things. All right, we're cool. All right, so now let's link them up. So head points to data equals, what was it set to, 420. Head points to next equals pi. You see that? This connects head to pi. There is now a link between, that's why it's called a linked list. And then we'll do the same for pi. So pi is going to be equal to 3, very biblical. Pi points to next is equal to meme. Links pi to meme. Meme points to, sorry, pi points to, meme points to data equals 96. Meme points to next equals tail. And then finally, tail points to data equals 21. Tail points to next is what? How do we indicate that we are at the end of the linked list? Null. Yeah, it's already set actually because we have it in the constructor. So we don't need to do we don't need to set it to null. So it's already set, but I'll just put it here for the sake of symmetry. Okay. So now we have a linked list. So now our linked list, let me pull the wrong monitor. So now what we did was we set the values, heads data, this is the data field, it's set to 420, and its next is no longer pointing at null, its next is now pointing at pi. So pi is pointing at this chunk of memory, head's pointing at this chunk of memory, head's next, this is its next field here, this is its data field. Its data field holds 420, its next field holds a copy of pi. So remember, a pointer is just a memory address. Like head might be memory address 8888, and pi is memory address 1600, and meme is need a number divisible by 8. Technically, all memory addresses on a 64-bit system are divisible by 8. 8080, and tail is at memory address 16. So all a pointer is really is just an integer. It's just a number. It's a spot in RAM. So somewhere inside of your RAM bank, there's a location there titled 8888, and you're saying, hey, at that memory location, there's two things at that memory location. There's a data, it's an int, 4 bytes, and there's a pointer, it's 8 bytes. And so set its data field to 420, set its next to whatever number this is. And so pi holds the number 1600. It's a terrible 0. 1600. And so next now holds the number 1600. That's all it is. But we don't talk about Bruno, right? We don't talk about the actual memory addresses ever. If you see it out, you're going to get some weird value. Like you can see it out if you want. Like if you see out, going to see out pointers. You can do it. I don't know why you would, but you can do it. The only time it matters is if you see a null, if you see a 0 in there. Then you're like, oh, pi is 0. Oops. You know. So, you know, that might be a reason why you'd print out. I went a little overboard here. Pi, meme, tail, and inline. And then if we want to point out the next pointers of each, head points to next, and pi points to next, and meme points to next, and tail points to next. And if you see why I like them, well, that's why I like them. Okay, so g++ main.cc to compile it. We run it, and here are the memory addresses. You can see they're all divisible by 8. No, you can't see that probably, but trust me, they are. Okay, so head is at memory address 55E75F29EEB0. This is in hex, so if you want to print out in decimal, but it's a number divisible by 8 if you care. I don't care. Like I said, like, we don't care, usually. Like, what are these actual numbers? We don't care. We don't talk about Bruno. We don't. But you can see that head's next is AED 0, and that is, what is that, pi, I think? So you can see that head points to next has the integer value that pi has. And pi's next holds the integer value of meme. And meme's next holds the memory address of tail, and tail's next holds 0. So the only time I actually pay attention really to memory addresses is if you get 0, they're like, oh, that's a null, right? Also, if you ever output the memory address of a stack allocated variable, it's going to be in a different chunk of RAM, and that's, I guess, vaguely interesting. Like if we have integer x equals 0, and we see out the address of x. You'll see that it is up at the top of the memory. So it's up higher in memory. That's the stack area right there. 7FF is the very top of memory. 55 is obviously quite a ways down. These are 64-bit numbers. So the heap is actually quite a ways down in memory from the stack, which is at the very top of memory. So so F is the number 15, D is the number 14, A is the number 10. We use hex for reasons you'll learn in 45, but basically a hex digit is 4 binary digits. And so 7 is 0, 1, 1. 0 plus 4 plus 2 plus 1. So it's a 0 and all ones. F is 1, 1, 1, 1. And so that's how I know that's the top of memory, because that's 0. Because if it's 1, it's negative. If the first digit's 1, it's a negative number. So 7 is 7FF is 0, 1, 1, 1, 1, 1, 1, 1, 1. It's the very top of memory. And then if I print out more stack allocated variables, you'll see they're all up at 7FF something. The heap is down below. So, like I said, we actually don't care about the actual memory addresses. I'm just printing them out as a, those memories are 8 bits long. No, they're 8 bytes long. They're 8 bytes long. If I said bits, I apologize. These are bytes. So a pointer is 8 bytes. It's a 64-bit number. So each head here is 12 bytes of memory. So when we say new list, lists, better way of putting it, this is 4 bytes for the data, and it's 8 bytes for the pointer. So this is not a very memory efficient data structure, right? You think about it. We have 8 bytes of overhead for every 4 bytes of data we're storing. So out of all the memory we are allocating on the linked list, 66% of it is wasted. 66% of it goes for overhead. So it's actually not a very memory efficient data structure. So that's something that's actually, if I allocate a gig of RAM, I want a gig of integers. I don't want to have a third of the gig of integers, right? I want a lot of integers. And if you allocated a gig of RAM for linked lists using this format here, only a third of it would actually be used to hold numbers. The rest of it would all be holding pointers. And this is only a singly linked list. You can also have a doubly linked list that has 2 pointers, in which case you'd have 16 bytes of overhead for every 4 bytes used, which is enormously inefficient. It's terrible. Okay. So we got ourselves, okay, so we've got this all linked up now. So pi's next is now pointing at meme over here. And so if you were to actually output that value, in this case I'm saying it's 8080, so that's the memory address of meme. And then meme's next is now pointing to tail. Tail's at memory address 16, which seems implausible to me, but whatever. 16 is now held in next, and okay. Okay. And then tails next is 0. So you can see right there, that's tails next right there. Okay, so we've got ourselves a linked list. You see how it's all linked up? And notice how I'm just kind of drawing it kind of like all over the place. And that's for a reason. That's because when you allocate memory, you have no guarantee that these nodes in the linked list are going to be next to each other. In fact, a lot of times they're not. They're just going to be over here and over here and over here. Whereas with a vector or an array, everything is contiguous in memory. Okay? And so if you have a vector or an array, dex to a lesser extent, all these numbers are like right next to each other in RAM. And that's nice for a couple of reasons. One, it allows you to just immediately be like, what's that number? And you do a little bit of arithmetic behind the scenes. You don't do it, the compiler does. It's like, all right, there's the value. And you can pull any value out of a vector in one step. Whereas if you wanted the third value out of this linked list, you have to start ahead, and then go to next, and then go to next, and then print the value. Which is terrible. That's why I hate linked lists. I don't hate them, but that's why I don't use them that often. Whereas with the vector, you're just like, hey, give me element 3. And it's like, all right, here you go. Boop. You know. So there's also a CSI 45 alert. This is a topic we talk about in CSI 45. But when you have things next to each other in memory, are fast. It's faster to have things next to each other in memory. And the reason for that is a CSI 45 topic, but the long and the short of it is if you've ever bought a CPU, it'll say something like it's got 16 megabytes of L2 cache, it's got 256K of L1 cache. Have you guys ever seen these things before? Like if you've ever looked at like buying a CPU or something, let's like go on to Newegg or something. I don't want to go too far down this rabbit hole, but it's actually kind of an important concept because it makes a huge difference in speed. Like it's an order of magnitude difference in speed a lot of times, and that's one of the reasons why I don't like lists. They're just slow. They're just slow. So right here, boom, 16 megs L3 cache, 4 megs L2 cache. So what happens, summarizing a whole lecture in one sentence, when you pull something in from memory, it pulls in things around it into memory as well. So when you read from RAM, it pulls all the things around it into cache, and then those are fast to access. Whereas with the linked list, if you pull this guy in over here, it's going to grab a bunch of stuff in memory around it, none of which is actually in the linked list. And so you don't get that benefit of cache hits and things like that. So, you guys kind of understand? Does that kind of make sense? Because I don't want to go too far down the CSI 45 rabbit hole, but it really does make like an order of magnitude performance difference. Like it'll run 10 times faster if your code is like next to each other in RAM versus like not. Okay. So over here we can see that they are next to each other in RAM, kind of a little bit, like 20 bytes away each one. So in this case they did happen to be next to each other in RAM, but there's no guarantee of that. We got lucky in this case. They're all next to each other. It's probably not luck. It's actually probably deliberate. Like it probably just allocates the next open spot, But once you start newing things and deleting things, like who knows, the next open spot might be over here, over here, over here. Okay. So does more cache make it more likely for things to be close together? No, but it means you can have more things in cache. So once you've kind of touched all of those nodes in the linked list, all of them will be in cache. And so if you like see out a linked list, and then you time it, and then you see it out again, the second time you see it out, it'll be an order of magnitude faster. It's going to be a lot faster because it's already in cache. So if you say for each element in a list, print it out, it'll be slow, much slower than a vector usually. Depends, you might get lucky. But the second time you do it, it'll be faster as long as it fits within cache, right? And so you saw there we had 16 megs of L3 cache. So if your list is bigger than 16 megs, sucks to be you. But if your list is small, meg or two, then it'll probably be held in cache. And that's why server CPUs typically have gargantuan cache sizes, by the way. So Now I am going down the rabbit hole a little bit, but like what I showed you was a desktop, but let's talk about CPUs, server CPUs, right? And so let's see here. Sort by price, highest price first. $23,000 for a CPU. $12,000 for a CPU. Ow! All right, so this one has 35 megs of cache. So, but can it run Crisis? Look at this one, 2.4 gigahertz. It's $5,800. Oof. Yeah, no thanks. Okay. Those are for servers, and the reason why they have that's why they're expensive in part because they have huge caches. And so, like if you're serving a web page, if you keep having to serve the same web page over and over again, if it's in cache, it's a lot faster. And so the bigger the cache is, the more web pages you can have in cache, and the faster you can be responsive to things. And so people will spend a lot of money for a lot of cache. So basically, all of CNN.com or whatever is in cache, and you can service the requirements really quickly out of cache rather than spinning up the hard drive and like, oh, what's the news of the day? That kind of stuff. All right. Put Crisis on the Nintendo Switch. Okay. Yeah, a lot of that is just for the cache. There's some other things as well, like error correcting RAM and things like that you sometimes upcharge for, because you don't want, like if you're a bank and a cosmic ray hits your bank account and adds an extra $1 billion to somebody's account, you don't want that to happen. You know what I mean? So you pay extra for like error correcting. So like if a cosmic ray, which it'll hit your RAM like 8 times a year. It'll flip a bit inside of your RAM, and on your PC you're just like, oh, it froze, reboot. But if you're a bank, you really don't want people's bank accounts just like bloop, 8 times a year. Seems like a bad idea. So they have things like error correcting RAM and things like that as well. Okay. So does it cost a lot to integrate a lot of cache into CPU? Yeah, and you'll learn all about that in 45 and why it's expensive and things like that as well. So this next part here, everyone pay attention if you've been tuning out because I was talking about cache money. That isn't very cache money of you. Nope, unrelated. This next part though is actually really important. So I'm going to make a dramatic pause here, and when you're all ready to see the most important thing, and I'm not being sarcastic here, this is actually the single most important thing to learn when it comes to linked lists. Make an emoji on chat. Oh, the drama. Hazelton, you already know this. You don't need to. You're in. All right. Okay, so big question. Let's take this part here. How do we traverse a list? So usually when you have a data structure, you want to do something like print out all the elements in it, right? Or add up all the values in it, or, you know what I mean? Like when you do a range-based for loop, for every element in a list, do something with that element. And so
It's cold in here.
it is cold in here. Let me turn off the.
Want to take a bite?
I'm all right, girl. Thank you. Okay, fine. Okay. Hey, just kind of spoiling the tension that I built up. All right. That's a good orange stuff. Okay. So how do you start at the beginning and go to the end and do something on every element of the list? Do you have a piece?
Sure.
Sure.
Take
We
it.
actually planted a Satsuma orange tree a couple days ago. So in a couple of years, hopefully, we'll have Satsuma oranges coming up. So I'm pretty excited for that. Okay.
Hopefully before I move schools.
Okay.
Well, if you're hungry, just get your own orange.
Move from one node to another sequentially. Exactly. So let's start with something basic. Let's print out all of the elements in the linked list. This is a code pattern that you need to engrave in your brain. You need to, like, remember when I taught you all for loop? Well, maybe not all of you had me for 40, but remember in 40 when I taught you a for loop, and I taught you this pattern here. Remember that? And I said, look, just memorize the pattern and you'll be good, right? Because if you don't, if you start at like 1 and, then you have to start counting your fingers and toes and it gets really complicated. So I'm going to teach you the same thing for linked list here. As long as you stick to the code, as long as you stick to the pattern, then you don't have to like explode your brain. Okay. What's a for loop? 4. List pointer temp equals head. Temp equals temp points to next. Cout temp points to data. End line. Let me run it. There's the numbers. I'm still printing the address of X. Review. Run it. 420, 3, 96, 21. Okay. 420, 3, 96, 21. So let's go through this. So we are making a new variable of type list pointer. If you want, I could make it like that so you can see it's a list pointer. I'm making a list pointer called temp. It actually doesn't matter to C++. You can do that if you want. In general, though, it's better to put it that way for reasons. So we create a new variable called temp, and we initialize it to head. And we say as long as temp is not null. Do you guys remember what null is? What number is null? Anyone remember? 0. In C++, what is false? What is false in C++ and C and other languages? 0. So, when temp becomes null, it becomes false, and the loop stops. So the highlighted code right there, oh my gosh, how many zeros? Okay, all right, enough. So this code says when temp becomes null, stop. Okay, that's what that means. It looks weird, right? It looks temp, but when temp becomes null, null is false. False stops the for loop. And then we print out we're going to start off with temp pointing to head. It's going to print out head's data. Then at the bottom of the loop, it says temp is equal to temp points to next. So it looks up head's next, which is pointing at pi. And so temp is now equal to pi. And then is pi null? No. Print out the data, so on and so forth. So let me switch over here, and we'll run through this on... let me erase the vector. Okay, so we are making a new variable called temp. It is a pointer. It holds memory addresses only of lists. And we initialize it to head, which is 8888. So we start off with temp equal to 8888, but we don't ever actually write numbers like that, ever. We draw it. And so we draw it this way. Temp is pointing towards head. Okay, so head is pointing at this chunk of memory here. Temp is pointing at this chunk of memory here now, because we said temp equals head. So when you say temp equals head, it just copies the memory value of head into temp. That's all it does. Because remember, pointers are just integers. That's all they are. Under the hood, they're just an integer. Integers are numbers, whole numbers. 5, 6, -2, but not things like 2.2 or 3.3.
The best here is a life hack. The best way to eat an orange is just to bite down into it. Don't peel it. It's just to bite down into it after you took the peel off.
Okay, good.
And then, but don't split the orange in half like this after you peeled it. Just bite it right away.
Like you're eating an apple.
Mm-hmm.
Is that why you have juice all over your face?
Who said I had juice all over my face?
I'm using my Sherlock Holmes powers right now to... Okay. So the for loop is this.
No, seriously, it actually is a good way to eat an orange.
Temp equals head. Temp.
Daddy, and by the way, I came in to tell
Temp
you that the
equals next. I'm just scribbling this really fast.
The floor in the kitchen is wet. I cleaned up. I spilled juice on it.
Close the door, girl, please. Thank you.
Okay, I won't talk about any more oranges. Or maybe I will.
Hey, did you eat your banana with or without the shell?
Huh?
Do you eat your banana with or without the shell?
It depends.
Okay, it depends. Okay.
It's
All right.
more I'll keep like the part that I'm not eating with the shell on. So.
Okay, all right, yeah, that's fair. Keep it safe from oxygen. Okay, so here we go. Let's run through the for loop by hand. Let's draw it out. Whenever you work with linked lists, it's always a good idea to sketch it out, to actually get out a piece of paper or a tablet or something and actually sketch what's happening on the screen. It's actually the only way of doing this where it'll kind of like make sense to you. So we start off with temp pointing at head. Is this a null pointer? Yes or no? Is temp pointing at 0? No, it's not a null pointer. Therefore, so we've checked that. Therefore, we see out temp points to data. Temp points to data in this case is 420, so it prints 420 into the screen. Then at the bottom of the loop, it says temp equals temp points to next. So temp's next is currently holding 1600. And so we say temp is equal to 1600. Right, but we don't actually write that. We just say temp is equal to temp points to next. And so temp is now pointing at pi. So temp and pi are 2 pointers that are pointing at the same thing. Same address in RAM. Okay. And we then see out temp points to data. See out's 3. We then check to see, and then we say temp equals temp points to next. So temp is now pointing to meme. This is not null either. Prints out temp points to data, prints out 96. Temp equals temp points to next. So temp is now pointing to tail. These pointers don't change at all, right? They're still there. We have a pointer that is starting at the top of the list and going to the bottom. It's just going down the line, hopping around through memory. And we see out temp points to data, prints out 21, and then we say temp equals temp points to next. And remember, temp points to next holds the number 0. So temp now equals 0. So is it true or false now? When temp equals 0, is it true or false now? It's false. So the for loop says, is it true or false? False. Okay, stop. And that's it. So the loop is done. The song is over. Thought I had something more to say. But that's it. That's really that is the whole pattern. This pattern right here will save your life someday. And by save your life, I mean like on a competency exam or something like that. So this pattern here is how you traverse a list. You start at the top, you go to the bottom, it won't crash, won't segfault, you won't have an off by 1 error. As long as you stick to the pattern, it's like the pattern for loops. You're not going to go out of bounds. You're not going to, you know what I mean? So it is analogous. Yeah, it actually is. Yeah, but it looks a little different. I++ is like this kind of, right? Like you're going to the next element, right? And you're checking to see if you're out of bounds. Yeah, you start at the beginning. Yeah. Don't you need to check to see if next is null pointer? Great question. So what if we did that? What if we said as long as temp points to next? What if we did that? We've broken the pattern. What if we require this? Off by 1. Look. Because we're stopping when our next pointer is null. That means when we get here, we move our pointer, so temp is pointing at tail. So we do the temp equals temp points to next. Then we check, hey, is our next null? Yes, it is. Quit. So we never print 21. Let's put 21 a little better in here. So we stop. We're stopping when our next pointer is null. And so we never print 21. So we have an off by 1 error. Likewise, doesn't read the data from tail. Yeah, because this print statement here takes place after the check, right? This happens at the top of the loop. We do this, then this part happens at the bottom of the loop. And so that's what I'm saying. Like if you break from the pattern, and you're like, all right, what if we started with head points to next, like this? And unfortunately, you might want to do that because the Zybooks, for whatever reason, had a dummy value at the beginning of a list. sort of philosophically opposed to that, but like they would actually do this, right? They would actually start with after the dummy value. But for our list here, what number is going to be printed first this time? Temp is pointing at who? So if we initialize temp to point at head points to next, which one of these 4 people here are we starting with? Why no dummy? I wanted to ask about that because it's terrible, and like they do that because they don't want to have to deal with the case of having a null pointer for head, right? Like we indicate an empty linked list by just having head be null, and they do it by having just a dummy. Like so their thing will always have head will never be null in their code because they always when they create the list, there's always at least one node in it, but it just wastes memory. It doesn't do anything. There's no point. It shortens their code, I guess, but then you have to do things like this, and I don't know, like trade-offs. I don't know. They're smart people down there in Riverside, so I can't really complain too much, but that is a difference between their code and my code here. Sus books. Okay, so what is temp going to start with? Here's the question. Oh, Burden's already answered it. Thank you, Burden. Yeah, temp is going to be initialized to pi, right? The second element in the list, because we're starting with head points to next. So we're starting with, so temp, when we start the loop now, temp is going to be pointing to pi. And so it's going to print 3, 96, 21, and then terminate. Yep. And I can, if you don't believe me, I can run it for you. So off by 1 error again. And so that's why I'm trying to tell you that this is the way, right? Like, in the previous class, I had Pirates of the Caribbean references and Monty Python references. In this one, we get Mandalorian, I guess. I don't know. So this is the way. Yeah, it's more of a guideline than a rule. I think I said that in the previous one. But really, it's not a rule, but you should probably stick to it. So that's how you traverse the list, and this will save your life someday. Okay, just memorize this. Now, what if you wanted to delete? What if you wanted to delete this list using a for loop rather than kind of like, does temp have to be set to head? Yeah, that's. Oh shit. Thank you. Yeah, of course it does. Oh right, I deleted it. Thank you, Mr. Shook. All right. So, right there we go. Let's find out what this does. Anyone want to take any guesses what's going to happen? What value is temp initialized to now? Huge error? Segfault? Error? I don't know. And literally that's the right answer. I don't know. Because this is a primitive type. Do primitive types initialize themselves in C++? Or do class objects with constructors initialize themselves? They don't. So this is going to be, it's just an int. It's going to have some int. Who knows? Whatever random integer is there in that variable, we are going to print out its data. And let's find out what's in RAM at some random memory address. This will be fun. It's like the lottery. Warning. Yeah, I know. This will be fun. Nothing. Okay. So that meant that the memory, it happened to be 0. And so it checked to see is temp 0. Yep. And it quit. So not very exciting. Not a crash, I'm afraid. But it might not have. It could have printed out some random number, right? And this is enormously scary. This is honestly one of the scariest things in computer science, which is an uninitialized variable. The reason why it's scary is that, like, it did nothing this time, but next time it might not. We could run it again even, and one of these times it might crash or it might print out random values. So in computer science, you want your code to work 100% of the time. And if it doesn't work 100% of the time, you want it to work 0% of the time. Like I said in the previous class, my brother-in-law is a software engineer also. You got a call in the middle of the night, server's down. It's crashing. We don't know why. So he leapt out of bed. He's like, oh my gosh. He starts getting dressed. He's about to get into his car, drive over. And they call him up again. Like, oh, don't worry about it. Stop. It started working again. And he was like, that's even worse. Like, if it was broken, I could at least maybe figure out what was causing it. But that means I got like an uninitialized variable in there or something. They're like, yeah, just turn it off, turn it back on. It started working again. It's fine. So that means somewhere in there's RAM that was just happened to be initialized to 0 like this, that one of the times it wasn't, and it crashed. And he's like, oh, Lord. He couldn't go back to sleep. He spent hours, poring over the code in the middle of the night trying to figure out where the undefined behavior is coming from. Yeah, it's scary. That's the kind of thing that just gets your heart racing, So, another thing, equals head. What if we did this? What if we did this? Did he find it? I think so. Just so this story has a happy ending. Most times it doesn't. We got millions of lines of code. You have no idea where it is. You have to use tools like Address Sanitizer to find these things. Always use Address Sanitizer when messing with pointers. Here's a pro tip. Okay. Hazelton, yeah, you want to post your name? It's Hazelton, you still here? Yeah. So when my students go to other colleges, apparently, like, other colleges just don't teach people about Address Sanitizer. I don't know. I'm sure some do, but like my students go there and they report back to me. They're like, yeah, nobody tells us about this stuff. And so you compile your code with g++/f sanitize equals address. This will tell you when you make a big oof. Okay? So if you screw up, Address Sanitizer will kill your program and be like, no. Line 33, main.cc, you have a memory leak. You have a use after free. You have a double free. You used uninitialized, whatever. Okay. So, yeah, there you go. Thank you, Hazelton. Yeah. So take this with you when you go off to other colleges, because apparently they just don't tell you about it. And it makes your life a lot nicer when it can actually tell you, there's your problem, line 42. Like, oh, thank you. Yes, you're right. That's a mistake. Thank you very much, Address Sanitizer, versus staring at your code for hours. Okay. So, infinite loop. So we have an infinite guess for infinite loop from Mitchell. Anyone else want to guess what's going to happen if we do this? Address Sanitizer is a C++ thing. It's built into every major compiler these days. It only came out about 5 or 6 years ago. Like, it's actually a pretty new thing, and it is a blessing upon us. Trust me when I say that these kinds of issues are the worst to deal with when your code works 99% of the time. It is so hard to track down. Address Sanitizer, just like, right there, you screwed up. You're like, oh, thank you. So nice. It slows your code down, so you don't always run it in production. But like when you're testing your code, yeah. Double segfault, infinite loop, never breaks, infinite loop. All right, let's find out. Let's find out what happens. Segfault. Okay, what happened? So it's not an infinite loop. Well, it looks like an infinite loop, but your operating system has a little safety measure. Because here's the thing. Your OS has been dealing with bad programmers for longer than you have been alive. It's simple truth. Okay? And by bad programmers, I mean all programmers, because we've all made this mistake. So if you ever try saying this, cout, all caps, if you ever try doing anything that essentially amounts to cout null pointer points to data or something like that, if you ever try doing that, you are doing what's called dereferencing a null pointer. And if you dereference a null pointer, the operating system detects the fact that you are trying to read from memory address 0 or thereabouts. And the operating system's like, nope. And the operating system will haul your program out behind the shed like Old Yeller and put a bullet inside. It will kill your program for you. If you ever try to access memory at a null pointer, segfault, segmentation violation, and corrupt. So it's called a segfault, a segmentation fault, because there are different segments of RAM that you have read and write access to. You do not have access to writing around 0. I call it kind of colloquially, I call it the minefield. So whenever I draw the memory map, like the stack and the heap and things like that, around 0, I draw a lot of landmines. And if you touch any of the memory around there, then it's segfaults. The operating system's like, no, you screwed up. You are dereferencing an old pointer somewhere in there. I know you're dereferencing an old port, and it kills your program, just like that. Okay. So MF Doom, yeah. So basically, it's brutal, but you remember it. So that's why it's segfaulting, is because we get to a point where temp is equal to null pointer, and then we say temp points to data. It tries reading from RAM at around 0, and the operating system is like, And that's actually a good thing. It's actually a nice feature. Because if you don't, like, who knows what you're going to get. Like, that means you're just off in la-la land, you're just reading and writing to RAM, who knows what is going to happen to you. There's a related concept called Fandango through core. Is there a faster way to add values to the list? Yeah, so you can, I don't know if we have time to talk about Fandango through core. But basically Fandango through core is when, like one of these values, let's say it has just like some wrong number in there. And so it jumps to that spot in RAM, and then it just interprets whatever's in RAM there. It could be your credit card number, it could be your social security number, and it prints out negative, whatever, and then your social security number, which is 1, 2, 3, 4, 5, 6, 7, 8. It just interprets your social security number as a RAM address, and it jumps over there, and it prints out whatever's there in RAM, and you happen to have a credit card number there, well, that's a RAM address, right? And it jumps over there, and it just starts printing random numbers out until you get lucky, and one of the chunks is 0, and then it tries following that, and it explodes. And so this is something that all old programmers have done at one point or another. You're printing out your list, you're printing out your list, you're printing out the list, and all of a sudden you get like 5 extra numbers that are just super wrong. Negative 9,250,000,000 segfault. And you're like, oops. Address Sanitizer will fix that for you as well. That's why Rust is popular. It's memory safe. Yeah, but here's the thing. Like, you don't need to go all the way to learn Rust if you use Address Sanitizer. Like, Address Sanitizer actually does a pretty fantastic job in verifying that your code doesn't have memory issues at runtime. Rust guarantees that at compile time, which is actually nice. So Rust is a good language. But I found that using Address Sanitizer and modern C++, like, I just don't have these issues anymore. Like, I literally just don't write code that segfaults anymore. Like, it's very rare. So it's like a ricocheting bullet. Yeah, it's just printing out, and at least we're not changing things, right? Imagine you're changing things, and you're just going through RAM, changing values. It's terrifying. Okay. So, is there a faster way to add values to the list? Sure. So let's talk about that. So, what if we wanted to add something to the head? Okay. So this would be like a push front. And today we're not making a whole class like methods and things like that. I'm just kind of going over the basics of linked lists. So I'm just going to do it right here. I'm just going to write the function right here. And I'm going to just add a new element to the front of the list. And so give me a number that you want to add to the front of the list. 45. Cool. All right, so list pointer temp equal new guy. I don't know. It doesn't matter. Equals new list. New guy's data that it holds. Its data payload is 45. And now, how do we link it up? Who should its next be? It's writing this to the front of the list, right? So let's see. Undo this Fandango through core here. Nope, ran out of undos. Fantastic. Okay. So we are making a new node that allocates the memory. I'm not deleting it yet, right? Which is a problem. I'm setting its value to 45. What should its next be set to? It should be set to head, right? So that's why I like drawing these things out, because every arrow you draw on there is like a line of code, right? So new guys, next is equal to head. And then head and tail are a little special. So invariants, if we're talking about invariants, and we haven't done a class yet, but head always points at the beginning and tail to the end. So if we want to maintain the invariant, I need to do what? What do I have to do to head? Because it's not the front anymore, so I need to maintain this invariant. What do I need to do so that head is pointing at the new beginning of the list? Head equals new guy. Yeah, just like that. That's it. And then if we run the code, I don't even know if this is going to segfault now. Yeah. Put this back here. Yep. And it's going to memory leak too. So, so you see 45, that's push front. That's it. Do you guys want to see how to do this in one line of code instead of, was it 4? I don't show it the compact way first because people's brains just start coming out of their ears and stuff like that. But a lot of these linked list things can actually be done in like one line of code. Like you can traverse, like traversing that linked list is like a single line for loop. Like I didn't even need angle, the curly braces, right? It's one line. So okay, so instead of doing all this, if we want to do this with a one-liner, head is equal to new list 45 head. There. And this works even if head was null to begin with, right? So the reason why this works, even if head was null, is because you notice how there's no dereference in here. There's no arrow, right? So this would work even if head is null. It just sets lists next to be null. So if we start off at the top just saying head is equal to null, this would set the new head's head to 45 and its next is null, meaning there's nobody after me. And then the second time you do this, in fact, let's just do this, right? Who needs all of you? Okay. So let's start off with list pointer head equals null. My background just changed. Null pointer. And let's build the list backwards. So numbers were, the last number was 21, 96, 3, 420, 45. So these 5 lines of code here are doing what all of this stuff up here is doing. We don't have names for the intermediates anymore, but we usually don't. Like, because that defeats the whole point of a data structure if you have to have a name for each node in the linked list. So we just have head in this case. No, and normally you'd have tail as well. So you'd do something like this. Head equals null pointer. Tail equals null pointer. Do something like that. So the tail doesn't change. If you're adding to the front, the tail doesn't change, right? The head keeps moving backwards. Every time you push to the front, it's going backwards. It's push front. Yeah, this is literally push front. But not a function. I'm just doing it in code. And if I run this, error pi is not declared. Yeah, okay. And I'm memory leaking right now, right? I got all these news. I don't have deletes. I am memory leaking for sure. Warning: tail is set but not used. Okay. Okay. So there you go. So here is the thing. It's the same thing, right? So I typically show it the more verbose way first, and then as you get comfortable with linked lists, like you can write these things very, very succinctly. Remember, every node in a linked list is itself a linked list, and it points to another linked list. So it's a recursive data structure. So this one points to nothing. This one points to the previous head. This one points to the previous head. This one points to the previous head. This one points to the previous head, and ends up that's the final head. So the final head is 45. Its next is the previous head, and so on and so forth. So if this confuses you, you can do the previous thing. But basically, it's just initializing the data and setting its next to be the previous head. And then all of that becomes the new head. And it works out just nicely and beautifully. Does that hurt your brain, or do you like it? Or and I know we're over time, but let me show you to delete it real fast. Okay, so deleting can be a little tricky. So I'm going to start off with the same code pattern here. Now, if I just did this, it would probably, this is wrong, by the way, but it would probably, you probably wouldn't notice it. You probably wouldn't notice it being wrong. But there's something really bad about this, which is that there's a rule that after you delete something, you can't use it, that memory again. Okay. You can reuse the variable, but like when you delete a chunk of memory, you can't use that chunk of memory anymore. It's off. It's undefined behavior. It's off limits. So, why is this bad? This deletes. You can't just delete the data. You have to unallocate the whole thing, or none of it. You can't delete part of it. But good idea. So what aspect of temp are we reading from after we've deleted it here? Because I'll tell you what the problem is. We're reading from this after we've deleted it. Next. Yeah, so after temp runs, it does this. So we delete temp, and then you set temp equal to temp points to next. That temp points to next is bad. And if we compile our code with address sanitizer turned on, fsanitize equals address main.cc, tail set is on, use your guys. Okay. Run, we get an address sanitizer explosion. Use after free. You see that? We deleted memory and then we used it. So it tells you immediately line 63 of main.cc, you done goofed. You done goofed. Them main.cc line 63. Right there. That's right there where the problem is. Okay. So the easiest way of handling this is just to make a temporary variable named temp2, I guess. So we grab the next first, we delete temp, and then we say temp equals temp2 or something like that. And in that case, we don't need any of you here. That's fine. Okay. And then that'll do it. Do you see what we're doing? So we're preserving the next value, and then we delete temp, and then we just set temp equal to that value. It's a little hackish looking, I guess. I don't know. You understand? So we can't use temp points to next after we've deleted temp, so we just save it first, and then we use it, the saved version. And if we do that, then no address sanitizer says you are A-OK. You're fine. You're good to go. All the news has been deleted. We can get rid of that to do. So you just save a copy of temp points to next. Then you delete temp, and then you use the copy. So it's a little tricky. It's not too bad. But you notice the code pattern's basically the same. Just I deleted this part of it because I'm moving the pointer like here, you know, because temp2 is temp points to next. If you see that, temp2 is temp points to next. So I'm kind of doing it by hand here. Normally it'd be there in the for loop, but I got nothing there. So that is linked lists, and we can go through the other operations on Friday. I do want to give you some lab time on Friday to work on the homework, but we can go over inserting in the middle and popping, deleting things, adding to the front, adding to the back. Go through the operations on it. And then your next homework assignment after this one will have you using linked lists. Okay. Any questions? Scale of 1 to 10. How complicated do you think this is? How hard is it to understand? 10 is maximum confusion and pain. 1 is, I got it. Not a big deal. Nil. Null. You're going to crash me. 8, 5, 7, 7, 6. Yeah. Yeah, and there's a lot of reasons for that. Pointers are just inherently hard for people to work with because we're used to just dealing with variables. But when you work with pointers, you're dealing with like the address of a variable instead. So it's like referring to people by like their street address. Like if I know that Otal lives at 1234 Main Street, rather than referring to him by name, I'd be like the person that lives at 1234 Main Street. And you're like, why don't you just use my name? But when you have a pointer, like that's literally what a pointer is. It's an address. It's like, Cruz lives at Segfault Avenue. So I'm like, yeah, the student that lives at Segfault Avenue. Rather than by name, right? And that extra level of indirection, just you're like, so if your brain hurts, don't worry about it. Every experienced programmer has taken this class, and all of us have segfaulted, and all of us have just been like, huh. And we sit down, we write code, and it crashes, and it's part of the process. It's part of the process. So part of computer science is having your brain stretch, right? Like feeling like your brain's stretching, encompassing, and growing. And this is one of those topics that'll do it for you. I feel like my brain's short-circuiting. Going to vacation on null pointer drive. Yeah. All right, so we're over time already. I apologize for that. But I did want to show deleting before you moved on. So I will see you all on Friday. Try to get as much of the project done as you can before then, because I will give you some lab time. I plan on lecturing for about an hour, and give you about an hour of lab time to work on the homework. So you know what you're going to get stuck on. Okay, and that is it. So got some extra wrinkles on your brain. All right, thanks everybody for coming out. I'll see you guys on Friday. Peace.